All right, welcome everybody to Thread and Mutex Day. So, main.cc, main3.cc. Okay. So let's talk about a common problem when you're doing multi-threading. And the common problem is that if you have a variable that is shared among multiple threads, then when you read and write to them at the same time, you can get contention. For example, one thread might read a value, add 10 to it, and then write the value. And another thread might be doing the same thing. Like maybe the first thread reads the value, the second thread updates it 1,000,000 times, and then the first thread writes the value. And then all that work gets completely undone. So this is a very common problem with multi-threading, and I'll first set up a situation where this will happen. We'll have a little global here called int counter, and we'll just say for int equals 0 I is less than 1,000,000 I is plus. Just like that, and we'll make a thread named USA that we'll call foo, and we will say USA join. So we're gonna waits for USA to finish. Okay, and then we will see out after. Okay, so we spawn off a thread. Main does its own thing. In this case, main just waits for the thread to spawn, so it's not very interesting yet. What value is this going to print to the screen? If you see out if you multi-thread see out, can you see out faster? You can see out things while doing computations, because see outing things is actually not very fast. So it's pretty common to have a separate I/O thread that's like reading from the keyboard, writing to the screen, and your actual computations are kind of taking place under the hood. Okay, so main.cc. If you're going to do multi-threading, you have to link with key thread. Yes. There we go. So 1,000,000. All right, 1,000,000 times it adds 1 to 0. So 1,000,000. Now, if we were to look at the source code for this, I think alias G++, I do have the optimizer turned on. So this code is probably replacing all of this code with add 1,000,000 to counter, right? So I'm actually going to unalias G++ and compile it again, and we'll get the same result because there's only one thread. Now, let's do this again, this time with a second thread named USB. And we'll have USB, there, universal serial bus. And so A and B are going to be spawned off. They'll both be running the function at the same time, reading and writing to counter. What is counter initialized to? I know you guys love C++ trivia. What value is counter initialized to? If you want to watch our previous video on C++ trivia, the students enjoyed it immensely. They said it was a life-changing experience that made them appreciate the beauty and the sophistication of the C++ language. Uninitialized, you'd be wrong. This is actually guaranteed to be initialized to 0. All globals, incidentally, are initialized to 0. Fun fact, only stack variables and heap variables would be uninitialized. This is actually guaranteed to be initialized to 0 because what happens is when you run the program, it blanks all the memory, so you can't read the passwords and accounting information from the previous guy, right? So, yeah, so that is actually guaranteed to be 0. All right, so we're going to spawn off 2 threads. They're both going to be reading and writing to counter at the same time. What number should this display when we run it? We've got 2 different threads, each of which are going to add 1,000,000 to counter. Star Wars Trivia Day, since it's Star Wars Day, nah. Although we did make a Star Wars joke in the previous class. What value should this print? The joke was, I want to make an AT&T Boba Cafe. AT&T, get it? Have AT&T Walkers, ATSTs, Boba Fett's, yeah, the usual. Okay, 2,000,000. It should be 2,000,000. It should be 2,000,000. But we don't get 2,000,000. We get a different number every time. Okay, and so Yeah, it's a problem, right? Because we're reading a value, writing one to it, writing the value, and we're doing it at the same time. And so you might read a value, and then the other guy might run 1,000 points, and then you come back in and overwrite it. You know, like you read 5, and then the other guy takes it up to 500,000, and then you come back into existence and you write 6, and all that work is gone. Right? Do you guys see what the problem is here? So if you ever have a shared, if you have a shared variable, shared variables between threads need some sort of synchronization, or bad things happen. Okay? So if you're ever having two threads that are reading and writing to the same variable, you need to synchronize them, otherwise, right? So there's two ways of doing this. So learning point number 1, use atomic variables. Atomic variables guarantee that every time you read and write to them, it takes place in a single operation. So you say, add 1 to that variable, and it can't be split in half. It's not like loading the value, adding 1, writing the value. It takes place, guaranteed by the architecture in the standard library, to take place in a single operation. And then it doesn't matter which of the threads adds 1 first, right? Because each of these things are atomic. They cannot be split. That's why they're called atomic, right? Atoms can't be split. That's just science, right? They're these small... Atoms are the smallest thing that exists. It's definitional. Right? That's why they're called atomic operations. They cannot be split. We've never split an atom in our lives. Okay, so atom bomb, baby. Yeah. A lot of good music in the Fallout soundtrack. Protons and neutrons and electrons, yeah. Okay, but that's why they're called atomic. So how do you use atomic? Well, you hashtag include atomic, and then you come down here and change an int to be an atomic int, and that's about it. Now you get 2 million every time. Pretty easy. Pretty easy, I think. Any questions about that? What's going on, girl? You want to say hi to my students? Just hiding? Okay. Any questions about that? So there's a pretty significant limitation on atomics, which is that only addition and subtraction are supported. So you can't do atomic anything else than addition and subtraction. So is there something weird you can do with these? Yeah, you can lock them. Basically, though, all you can really do is add and subtract with it. So, yeah, pretty limited. So, about it, for something like this, it works. You know. All right. Do all primitives support an atomic state mode of themselves? I think just integers. I don't think floats do. Oh, maybe that is. No. Guess not. All right. Yeah. No atomic float. Just nets. So pretty limited. But if you need it, you need it, and it'll work in a situation like that. Okay, girl. Stop grossing out my students. Atomic character. Yeah, you can do an atomic character. Yeah, actually. Atomic character. Sure. Why not? Okay. There you go. That's an atom bomb. It's the nuclear particles left over after the fallout, actually. When would you use something like this? Anytime you do multithreading. I mean, my master's degree was specializing in parallel processing. Okay, and threads are the easiest way, I would say, to do it. There's maybe one other easy way of doing multithreading, which is to use something called OpenMP, where you can basically just tag a for loop as like be parallel, and then the system will run it in parallel for you. So if you're going to be doing like a bunch of addition like that, you just basically say run it in parallel, and then the thing will look at how many CPUs you have on your system. I got 10 CPUs and 20 hardware threads, so it'll spawn off the threads for you. OpenMP is probably the easiest way of doing parallel processing. This is pretty easy though. But the trouble is, if you've got a bunch of threads that are all reading and writing to the same value, you need to synchronize them. And atomics are limited to just really addition and subtraction. So, for trivia night, So there's a better thing if you wanted to do better things. So for example, learning point number 2, use mutex and walks. Okay, so in order to do this, you have to hashtag include mutex. Like that. Okay, and so what are you doing, girl? Ada, I'm gonna melt if the AC's on right now. All right, so mutex. Let's see, my lock. Let's see if that works. Okay, and then here I'm gonna say, yeah, let's do like a float. Like you were asking about floats, we'll have float f. That's initialized to 0, and so rather than using counter, yeah, heck, we can do both. Why not? Okay. And say f is equal to plus equals 1.1. All right. All right. So now, let's put this back at atomic int, and we're going to output counter and f. And let's spawn off a couple more threads too, because why not, right? So in addition to the United States of America and the Universal Serial Bus, we're going to add the University of Southern California, or as my USD friends sometimes say, the University of Spoiled Children, and the University of San Diego. So we got 4 threads now. Okay, each thread is going to add 1 to the atomic counter, so we should get 4 million out of it, and it's going to add 1 to the floating point number. So, yeah, I don't know. Let's 0.1 maybe. There you go. So, I don't know what that is. We're getting different numbers every time though with the float, right? Because we're not synchronizing on that. Is there like a check-in, check-out method where you can only check a variable if it's in and checks it out? Yep, that's exactly what we're about to do. So we're going to do. It's like when you go to the restroom, right? And at like a gas station, right? And you go up to the front. You're like, hey, could I get the key? And they hand you a key, and there's like a stick with dubious colors on it. And you gingerly take the stick with the key, and you go out to the side, and then somebody else goes in. They're like, hey, can I use the restroom? They're like, sorry, you have to wait. There's a person in there already. And that's what we're going to do. So we can say lock guard of type mutex called perchance on my lock. And that's it. So now it's synchronized. So mutex stands for mutual exclusion. Mutex equals mutual exclusion, meaning only one thread can be in this at one time. So mutexes are used to mutually exclude different threads from the same block of code. So we've got 4 different threads will all be running. When the first thread comes in here, they go up to the gas station attendant and they get the key to the restroom, and then they go into the restroom. And then the next thread and the next thread and the next thread all come in. They're like, hey, we want the key to the restroom. And the gas station attendant's like, you have to wait. And so they just sit there and they wait. When they get to this line, if that lock is already taken, if that key, if it's locked, then they just sit there and wait. And then once the first thread finishes and comes back and gives the key back, then the gas station attendant hands it to the next person, and so on and so forth. So if we want, we can see the order these things are coming in. So cout thread finished. And we can actually pass a parameter to a thread like this. Okay. And so you can see that thread 0 finished, thread 1 finished, thread 2 finished, 3 finished. Oh, I just ran a assembler. Let's not do that. And you can see we get the same result every time. Now, it's not really multi-threaded anymore. That's maybe a problem. So, you know, basically these guys are all serialized because none of them will run in parallel at the same time. So why bother, right? Well, because we don't have to have them all blocked by the same chunk of code, right? So what we could do is we could split this for loop here to two parts. And the first part could do the integer, and the second part could do the float, right? So all four of them will be going at the same time on the integer, but maybe one of them finishes first. And then they can get going on the float, you know? And maybe they can get all the way through the float by the time the other guys get to it. So this might be faster. And it's still synchronized. You can see that they finish in different orders now, right? Whereas before they always finish 0, 1, 2, 3 because when you spawn a thread, it's the first one that's going to run, and it's going to acquire the lock. And the next guy to run is going to run next. And so before it was 0 finishes, 1 finishes, 2 finishes, 3 finishes. Now it's just kind of like whoever finishes the first part first, gets the finish line first, acquires the lock at the restroom, goes into the restroom. Then whoever gets in second has to wait in line. Okay? Gas station bathroom. There you go. So it locks it when you get to this line here. Okay? So when you get to this line, that's when you acquire the lock. Everything above that can run in parallel. This thing here prevents... so when does this release the lock? It releases the lock here. There is a destructor on lock guard that releases the lock. Okay? So when it goes out of scope, it releases it. It returns the key to the gas station attendant, and then the next person can take the lock if there's anyone waiting. Can you unlock it manually? Well, you can do something like this. Okay. Because generally speaking, lock guards are simple. There's more complicated things you can do, but they're simple. When you create them, it acquires the lock. When they go out of scope, they release the lock. And so if you want to manually release them, the easiest way is actually just put them in their own scope. And C++ trivia, which I know you guys love, you don't need an excuse to make a scope. Right? Like some people might go like, if true, you know, or something like that. You don't need to.
Daddy,
you don't need to. You just do that.
What you should do with your students? You should do a Kahoot with them.
That's exactly what they're saying. We just did a Kahoot, but it was on Discord, essentially. Yeah, you just have a scope, like whenever you want. And so it just goes out of scope here. Yeah. So this will prevent multiple threads from writing high at the same time. And in fact, this is, I mean, high is not really a big deal. But if you were to... do something like this. You can't really see here, but if you're writing to a file, you really don't want another thread writing to the file at the same time, right? You're writing out your social security information, Bill Kearney, social security number 1, 2, 3, 4. That's like Bob, because another thread comes in and starts writing Bob's information right in the middle of your database. You absolutely do not want that. So if you're ever writing to like a file with multiple threads, and multiple threads can all write to the same file, it's very common to acquire a lock on the file, and then you write out your record or whatever it is you want to write out, and then you release the lock, and you close the file, release the lock, and then another thread can open it, usually in a pinned mode, so it doesn't erase what was there before. It jumps to the end of the file and then, you know, adds on to it. So usually when you're doing file I/O, very important to use mutexes, so that only one thread could be writing to the same file at a time. Now you can have each thread like write to its own file. You know, that's a perfectly valid way of doing things, right? Another way of doing this would be you create an array of floats, right? So rather than having one float, you can have a float array of size 4. And then rather than doing this thing here, oh, this is not synchronized anymore, right? Rather than doing that, you can do this. Okay. So we've got we've got now an array float. So each thread has its own private variable, essentially. So none of them are writing to the same value at the same time. They're all just accumulating data into one particular variable. And then at the end of the day, we can add these all up here. Cout. Whatever. Okay. Accumulate from r dot begin r and r 0.0. Accumulate is in numeric. Yeah, it's in numeric. Okay. And so you can see, because each of the threads is writing to its own private variable, they don't step on each other's feet. You don't need to have any lock at all. You just write to the thing, and at the very end, you accumulate across that array, which is a very trivial and easy task to do. It's 4 additions, right? And so, does this make sense to you all? So basically, it's very common to just like not have one variable that everybody shares, but one variable per thread, and this should be like a constant, but whatever. You get what I'm getting at here. And so they each write to the end, and then at the end you do like a reduce or an accumulate step where you add all the things together, and there you go. There's the addition. So used in image processing, yeah, all the time. Like a lot of my code was working over 2D arrays, and so you have a 2D array that's like 1,000,000 by 1,000,000 or something, some gargantuan array, right? You can't even hold it in RAM, really, right? And they're doubles, right? So that's quite a bit of memory. And so what you do is you split it out over 1,000 different computers, right? So you say, all right, thread 0, not really a thread, you run it on a different computer, it's not even a thread. Computer 0, you get this chunk of the array. Computer 1, you get the neighboring chunk of the array. Computer 2, you get the net chunk of the array. And so you split out the array across all these processors. And then they do a chunk of work. And then they communicate their results to their neighbors, usually. And then the neighbors do their things, and they communicate with their neighbors. And all these computers are running at the same time. And there's a lot of different ways you could do, like load balancing to make sure that the thing stays relatively even among the different processors. But, in an ideal situation, you'll get somewhere, if you have 1,000 processors, you're not going to get 1,000 times performance, because there's all the communication out to scatter, and then all the communication back to gather, and stuff like that. But maybe you'll get like a 500 times speed up, something like that, across 1,000 processors. Who knows? It depends on the task. But for really big things where you can't even fit a thing in RAM, like you just split it up and parcel it out, and each computer has a gig of RAM or whatever, and then all told they're processing a terabyte array in chunks, and they're all doing their thing and communicating, and then when it's finished, they all send it back to main, and then main will accumulate the data into one result and present it to the user. So that's not something we're going to do in this class. Like I said, I took this was my specialization. I took 2 undergrad classes in it. I took 2 graduate classes in it. I did 3 years of research in it. Like it's a whole thing you can get into. But I think that threads are pretty easy, right? Like you just create a thread, name the thread, give the function that runs. You can pass parameters to it if you want, and then they can just all kind of work at the same time and do stuff at the same time. And if you need them to synchronize, this is the way to synchronize them. So. Point number 1, atomics. Point number 2, mutexes. And thread local variable. It's not really a thread local, thread specific variables. So each thread has, you could actually, you know what I mean. So basically each one of the threads has its own part of the array that it reads and writes to exclusively, so it doesn't step on anyone's fingers. Okay. What was detach doing? So detach means run, and I don't care about you anymore. And so if I were to detach these threads rather than joining them, So if I were to detach these threads instead of joining them, then I'll just run it. We're getting no answers. Because what happens is that main spawns these threads, then after it detaches them, it just keeps going. It doesn't wait for them to finish. And so it just prints out whatever value counter has, and main just keeps going. These threads are doing their own thing. They're adding things. Who cares? You know? And so it might be actually fun to do this in a while true loop. Yeah, you see this. Standard library. And so you can see main, as main's running, you can see it watching the value of counter going up. Kind of cool, right? Every 1,000 microseconds. And then one of the threads has started doing F. And then these guys, there's a couple threads still on the integer part. And then now all the integer part's done. Now they're all working on F. Thread 1 finished there. That's done. And then thread 2, thread 3 finished. And now it's in an infinite loop. Because it never stops, right? So you can't tell when the thing is done because you've detached them, right? So join waits and no wait, right? Yeah, the next assignment's going to be using multi-threading. So don't worry about it for now, though. Okay. All right, so that's it for today. Hope you guys enjoyed the trivia night, and hope you enjoyed multi-threading. Different solutions for the synchronization problem. 3 different ways of doing it. 3, don't step on each other's toes. Right, just instead of having one bathroom that people have to share, have 4 different bathrooms. Person A gets bathroom 1, person B gets bathroom 2, and then you can go in and go out whenever you want. Okay. So that's it. I will see you guys on Friday. Peace.